Good morning and welcome to the class on digital signal processing. In the previous video lectures, I have explained you mapping techniques from S-plane to Z-plane. They are mapping of differentials and impulse invariant mapping. These two mapping techniques are simple, but they are used to design only low pass filters and band pass filters. To overcome this limitation, in this lecture, I will explain you a mapping technique from S-plane to Z-plane known as bilinear transformation. Bilinear transformation is a conformal mapping. That is, this mapping will map the j omega axis onto the Z-plane to the unit circle only once and preserves the angles. Secondly, this mapping maps the left half of the S-plane to the inside of the unit circle. That is, a stable analog filter will be converted to a stable digital filter. And the right half of the S-plane is mapped onto the exterior of the unit circle. So these are the certain important conditions that are to be satisfied by a mapping technique. So bilinear transformation possesses all these properties. Now I will explain you the bilinear transformation method. Consider an analog filter H of S that is linear, defined as B by S plus A. So this is the transfer function of an analog linear filter. Now y of s by x of s is equal to b by s plus a. So s plus a times y of s is equal to b times x of s. So this can be rewritten as s times y of s plus a times y of s is equal to b times x of s. Now if I apply the inverse Laplace transform to this, then we are going to get s times y of s is nothing but dy of t by dt plus a times y of t is equal to b times x of t. If you look at this particular differential equation, this is of order 1. First order differential equation describing the transfer function of a linear filter. From this differential equation, we need to find the value of y of t. So, one approach is to approximate this differential equation with a difference equation. Instead of this approach, we try to integrate the differentiation and approximate that integration with trapezoidal formula. That is, y dash of tau integrated from t0 to t d tau plus the initial value y of t naught, and this one will be the y of t. So here we have integrated the differentiation and plus the initial value to obtain the y of t. Now this integration now will be approximated by the trapezoidal formula. So we will take the values at t is equal to nt and t0 is equal to nt minus t. At these intervals, we will evaluate this integral using the trapezoidal formula. So y of t is equal to t by 2 y dash of nt plus y dash of nt minus t plus y of t0 is nt minus t. So this is the value of y of t by using the trapezoidal formula evaluated at t is equal to nt and t naught is equal to nt minus t, where capital T is the step or length of the interval. Now we will evaluate this particular differential equation at t is equal to nt. So y of y dash of nt plus a y of nt is equal to b times x of nt. So here y dash of nt is equal to minus a y of nt plus b times x of nt. This is equation 1. We have obtained this equation evaluating this first order differential equation at t is equal to nt. Next, we will evaluate the same differential equation at t is equal to nt minus t. Thereby, y dash of nt minus t is equal to minus a y of nt minus t plus b times x of nt minus t. So this is equation 2. Now we will substitute equation 1 and equation 2 into this equation and we will get the value of y of t. This equation is the trapezoidal approximation of the integration of the derivative, and this equation we have obtained by substituting t is equal to nt in the first order differential equation, and that is equation 1, and this we have obtained the value at t is equal to nt minus t in the same first order differential equation. Now we will substitute equation 1 and equation 2 into their respective places and we try to find the value of y of nt. So y of nt is equal to t by 2. Here y dash of nt, that is first derivative evaluated at t is equal to nt minus a y of nt plus b x of nt. Next plus, so next one is derivative evaluated at t is equal to nt minus t, and that is equation 2. So minus a y of nt minus t plus b x of nt minus t, and plus the value at y of at t is equal to t naught, that is y of nt minus t. Now we will group the y terms to the left hand side and x terms to the right hand side. Thereby y of nt, bring this term to the left side, it is plus at by 2 y of nt. Next this term minus a t by 2 becomes plus, so a t by 2 y of nt minus t, and this term, so minus y of nt minus t. This is equal to x terms are, this is the first term bt by 2, so it is bt by 2 x of nt plus bt by 2 x of nt minus t. Now we will approximate the y of nt to be equal to y of n, and y of nt minus t approximately to y of n minus 1. Similarly, we will approximate the x also. Now y of n plus at by 2 y of n plus at by 2 y of n minus 1 minus y n minus 1 is equal to bt by 2. We get the common, it is x of n plus x of n minus 1. Now group the y of n terms. Now apply the z transform to this equation. Then we are going to get y of z plus at by 2 y of z plus z power minus 1 at by 2 y of z minus z power minus 1 y of z is equal to bt by 2 x of z plus z power minus 1 x of z. If we get the y of z term common, so it is y of z, so 1 plus at by 2. Here it is being minus common, so it becomes 1 minus at by 2, 1 minus at by 2 z power minus 1 is equal to bt by 2 1 plus z power minus 1 x of z. From this equation, y of z by x of z is referred as h of z. This is the transfer function in the digital domain. H of z is equal to bt by 2 1 plus z power minus 1 divided by 1 plus at by 2 minus z power minus 1 plus at by 2 z power minus 1. From this equation, b times t by 2 times 1 plus z power minus 1 by, group these two terms, 1 minus z power minus 1, group these two terms, thereby we are going to get plus at by 2 1 plus z power minus 1. Right? Now keep the b term here and 1 minus z power minus 1 by t by 2 1 plus z power minus 1 plus a times t by 2 times 1 plus z power minus 1 by t by 2 1 plus z power minus 1 is equal to b by, this one is 2 by t 1 minus z power minus 1 by 1 plus z power minus 1, and this one is plus 1 plus z power minus 1, t by 2 gets cancels, so it is plus a. So this is h of z. Now compare this h of z with h of s. So this is equal to b by s plus a. Upon comparing this h of z with this h of s, we see that the numerator terms are b and b. In the denominator also, the first term is here s and here the term is 2 by t 1 minus z power minus 1 by 1 plus z power minus 1 plus a and plus a. So we can say that the mapping from s plane to z plane is given by s is equal to 2 by t 1 minus z power minus 1 by 1 plus z power minus 1, and this one is the bilinear mapping of the variable from the s plane
to z plane.